Hi, welcome back, college algebra students. This is Miss Backfish again, and I just wanted to pick up where we left off in section 4.4. I was planning to continue the video, but unfortunately my computer had other plans. So this is a section on equations, exponential and logarithmic equations. And in the other video, we had done exponential equations where we looked for whether or not we could put take the two bases and rewrite them as powers of the same number, powers of the same base. So in other words, 32 became 2 to the 5th and 8 became 2 to the 3rd. They're both 2 to something. So that was our first strategy with exponential equations. Notice there aren't any logarithms here on this page. Then we did another exponentials. And this time we were taking the log of both sides. That was our strategy. Again, there's nothing log here. It starts out just exponential equations. Next up, we had gone ahead and talked about the first of our types of logarithmic equations. And on all of these, notice, we had logs only on one side of the equation. Sometimes it was by itself. That was the goal. We wanted to get it, well, I don't write it on here, but we wanted to get it to where it was just log base something of something equals something. We wanted to get it in that format first, and then we were solving by rewriting. All right, so we rewrote as an exponential and went from there on all of these examples. But again, the thing to remember about these were that we only had a log on one side of the equation, or multiple logs, but we could put these together so that we could get it in that form, where it was just a basic log equation. Log base something of something equals something. All right, so we were able to get it in that form here. Next up, we're looking at equations where you have logs on both sides. Okay? And we're using what is called the way of logarithms, or the fact that it's one-to-one, to say this. Whoa, sorry. If I can get the log, two logs, basically the same base, log base whatever of m equals log base whatever of n, then these two things have to equal. It's a lot like when we said if you have 2 to the x equals 2 to the 7, then x must equal 7. Sometimes students like to say you're canceling the 2's. You're not really canceling them. You're just observing that if this is true, then this has to be true. And the same thing goes here. If log base 10 of x equals log base 10 of 12, then x has to be 12. It's usually not going to look quite that simple, but that's the idea. Okay? So we're going to get it to where it's a log expression on one side, basically like this. Log expression on one side, log expression on the other side. Just one log on each side. You're not going to have log plus log or log minus log. If you do, you want to combine them. You want to condense that expression. Has to be the same base. Okay, so first off, I have to condense this expression. I need to get down to a single log. I'm going to take that 2, pop it up into the exponent, and I have log base 10. There's no base written there, so it's a common log. This is log of x squared minus log of 7. And that's log of x squared over 7. Quotient rule. Equals, and on the other side we just have log of 112. Well, if the log base 10 of all of this, use my colored pencils, if the log base 10 of all of this equals the log base 10 of all of this, or this, then these two things have to be equivalent. X squared over 7 must equal 112. So I'm going to solve that by first multiplying both sides by 7. And that gives me x squared, let's come up here a little bit, x squared equals 784. And square root of 784 is 28. Now technically, since we introduced the radical here, technically I would usually say then x is plus or minus the square root of 784. So x is plus or minus 28. But I glanced up here and said, remember, we can't have the log of a negative number. So x can't be negative 28. So it's just going to be positive 28. Okay, and as always, if we can check them, we want to. And if you notice, every single one of these on this page is can check them, and we want to. When it's a log equation, we want to check the answers to logarithmic equations because the log function does not have an unlimited domain. There are limits on what can be in the domain. But notice all of these on this whole page are common logs, log base 10, so that makes them easier to check in our calculator. So I can go back up here and plug in 28 and say 2 log 28, close parentheses, minus log 7, close parentheses. That's what I get when I do that, and then evaluate the other side, log 112. Got the same thing, and therefore x is 28 works. All right, next up. Again, the goal here is to get it one log expression on each side. Let's do this. So over here I have 2 log expressions. I'm going to need to put those together. So I've got log 5x plus 1, it's log base 10, equals, this is addition, that goes together as multiplication. So log of, it's 2x plus 3 times 2. I'm going to put the 2 out in front. So now we have just one log expression on both sides. They're the same base. And so again, if log of this equals the same log of this, then what's in those 2 blue boxes must be equal. And I'm going to see if I can make this stop glitching a little bit here. I don't know if you'll consider it worth the trade-off. I've got less resolution, but it shouldn't glitch as much now. So 5x plus 1 equals 2 times 2x is 4x, 2 times 3 is 6. And then I just solve, and I get x equals 5. Then I'm going to go back up here and plug in to check, because it's a log equation. So log of, 5 times 5 is 25 plus 1. So that would be 26. And over here, I've got log of 2 times 5 is 10 plus 3, also 26. So yeah, it's going to work. Same thing, 2 more. Add, so this is going to go together as multiplication. So I have log of 2x minus 1 equals log of 3 times x plus 3. So 2x minus 1 equals 3 times x plus 3 times 3. When I solve that, I get negative 10. Okay, so let's look at this. On the left-hand side, log of 2 times negative 10 minus 1. Domain error. So this is not going to work. All right, so therefore we're going to say we don't have any other solutions, so that's it. That's an extraneous solution, and we'll just say there are no solutions. Next up, this is also a plus, so multiplication. Log of x times x plus 3 equals log of 10. Now, remember, this means log base 10. So log base 10 of 10, this whole thing over here is just 1. I don't really know that that helped me to do that. That's just my instinct. It really didn't help. There's really no reason to do that in this situation, because I'm about to get rid of those logs anyway. But I always jump right there when I see this situation. So let's go back. Let's pretend I didn't do that. Let's reinstate the log of 10, because then I can say x times x plus 3, the quantity x plus 3, equals 10. So x times x plus 3 equals 10. X squared plus 3x. Bring the 10 over. to make it equal to 0 on the right. And then I like to solve by factoring when I can. So this one is factorable, x plus 5, x minus 2. And then each of those factors gets set equal to 0. So that gives me x is negative 5, and it gives me x is 2. So I'm going to go back and check now. I'm suspecting, since I got two solutions, I bet I'm going to end up throwing one out, but we'll see. Maybe not. Well, right away we can see, can't we? Log of negative number, that does not fly. Okay? Log of a negative doesn't work. This is extraneous. It's nice to write that on there, extraneous. And then let's try 2. Log of 2 plus log of 2 plus 3. That's 1, which is also what I said log of 10 was just a second ago. So that's right. Okay, last one. We've done 2 with exponential equations, 2 strategies with logarithmic equations, and then actually this one is sort of both, sort of kind of both. This is dealing with our most common scenario for exponential equations, which is compound interest. Okay, this is the standard compound interest formula. Remember that A is usually what we say final amount. P is the principal, which means the original amount invested. R is the rate, meaning the interest rate. It's the annual interest rate, like for the whole year. N is the number of times per year you're calculating the interest or compounding. And T is how long this investment is happening, how long you leave your money in there. Okay, so find out how long it takes an investment of $5,000. There's P. To grow to $9,000, that's what we want it to be. So that's our final amount. If it is invested at 14.7%, we always change percentages to a decimal, and that's R. Compounded daily, that tells me how many times per year. In this case, N, number of times per year, is 365. We don't go with a leap year. Okay, so filling into this formula is what I want to do. 9,000 equals 5,000 times 1 plus 0.147 over 365, all to the 365. And what it's asking is how long, that's T. Okay, this is the very scenario that is why, and I feel like we need logarithmic equations, is if we need to solve things that are in the exponent, how do we get them out of the exponent? That's the answer. We rewrite it as a logarithmic. So let's figure out what we're going to do here. Be careful that you remember that this number is being raised to a power. This number is not. So we can't put these together. Exponents come before multiplication. So I have to deal with all of this as one unit. I cannot multiply the 5,000 times whatever I get here. But I do want to know what I get there. I would like to change that to a simpler expression. So 0.147 divided by 365 added to 1 gives me 1.0004. Let's just stick with that. To the 365t. Okay. So again, I may not be able to multiply that by 5,000, but I can do something with the 5,000. I can get it off of that side. Anytime we're trying to solve an exponential equation like this, one where we clearly can't write both sides as powers of the same base, we want to get it in that simplest of forms of an exponential. Something to a power equals whatever. So that's what I'm going for here. One side should just have something to a power. Okay, so 9,000 divided by 5,000, 9/5. 9/5 is 1.8. So this is what I have at this point. Okay. If you feel better, you could put the exponential part on the left and the number on the right. But if I'm going to rewrite this as a log base answer equals exponent, I could do that. I could also do this by taking the natural log of both sides. This one I could do either way. So let's do both ways. If I rewrite it, here's the base, here's the exponent, and here's what we call the answer. So it becomes log base answer equals exponent. That's it, the rewritten form, the logarithmic form of this equation. And then what I would do probably is use the change of base formula. I knew there was one. There was one we didn't put on our properties list. This was our list of all the properties on this lesson that we've been talking about in this unit, actually, from the last video. And let's go ahead and put the change of base formula. We did not add that. Change of base formula allows me to change a logarithmic expression to any base I want to. So let's say it's log base b of m. I could change it to a base 4. I could change it to a base 17. I could change it to a base 325. But if I can change it to any base I want to change it to, which the actual rule looks like this, meaning A is that any base I actually want to, then why not change it to either natural log or common log because they're in my calculator. So that's what we use it for. Okay, we use it to change a logarithmic expression into either log over log. And notice the number that is originally higher up goes on top. The number that is originally lower goes down the bottom. Or we could do the same thing with natural log. Okay, so in this particular problem, I'm just going to, I don't know, it doesn't really matter. I'm going to use natural log. I'm going to take this expression and say, okay, that's the same as natural log of 1.8 over natural log of 1.0004. That's supposed to be equal to 365 times t. So I'm going to do this in my calculator and then divide it by 365. So natural log 1.8, close parentheses, close parentheses. That's what that gives me. Divide it. That's what over here. T isn't alone until I've divided both sides by 365. And now T is alone, and it says a little bit more than 4 years. 4.03 years. So just over 4 years, I think is what I'm going to say. All right, now I did that using rewriting. I took an exponential equation and I rewrote it as a logarithmic equation and then solved. I told you at this point right here we could have just done it by taking the natural log of both sides. So let's try it that way. I would have just done this. And then, oh, sorry, I didn't realize I was going off the page. The reason we do that, or the reason that's helpful, I guess is the better way to say it, is that when you have an exponent, you can move it out front of a logarithmic expression. So this gives me natural log of 1.8 equals 365t times natural log of 1.0004. So trying to get t alone means I can divide both sides by natural log 1.0004. And then, once I get that, I'm going to divide both sides by 365. Notice it's the same thing that's right here at this point. So either one of those strategies works. Rewriting it in a logarithmic form or taking the log of both sides. We'll get the exact same answer. All right, down here we have the formula A equals 37.3 times e to the 0.0095t power models the population of California in millions t years after 2010. What was the population of California in 2010? Okay. Is that 3 zeros or 2? I think it's 2, sorry. 95t. Okay, this is what we have. If t is the number of years since 2010, then in 2010, t would be 0. If we put a 0 in here, this whole exponent becomes 0. E to the 0 is what? It's the same as anything else to the 0. So when t is 0, we get 37.3 times e to the 0, which is just 1. So that's 37.3 million people. That's part A. Part B is when will the population reach 40 million? So they mean when will the final amount be 40 million? So that means when will A be 40 million? So we're going back to this. We're not plugging in t as 0 anymore. We're asking when, so we don't know what t is. We're going to plug in 40 here because this is in terms of millions. It's at 37.3 million now. We want to know how long it takes to get 40 million. Okay, so we've got 40 equals 37.3 e to the 0.0095 t. First thing I'm going to do is get the exponential part alone on one side. And I'm going to go ahead and divide that, make it a little bit easier to work with. 40 divided by 37.3 is 1.072. Let's leave it, let's go with that many decimals. So 1.072 equals e to the 0.0095t. I'm going to turn this around just because we do tend to like to do that, to have the exponential part over on the left. It doesn't matter. It's just a habit. Okay, so this is something I could solve by, sorry, that was another intercom break. Okay, we could do it by either rewriting this in logarithmic form, or by taking the natural log of both sides, or common log, any log. But I think I'm going to take the natural log of both sides because if I take the natural log of an e, that will simplify nicely. So let's see how that works. Natural log of e to the 0.0095t equals natural log of 1.072. Okay, natural log means log base e. So base e, and then there's an e. So this whole thing becomes just 0.0095t. And since I'm trying to find out what t is, I want to get t alone. So that's what goes in my calculator in order to make that happen. So I've got natural log 1.072 all divided by 0.0095. Make sure you put your parentheses in there. And I get 7.3185. So 7.32 and this is when will the population of California reach 40 million? Okay, so T means how many years after 2010. So we're talking about 2010 plus 7.32 years. So depending on how specific you're expected to be, you could say in 2017, sometime in 2017, or you could say 0.32 is how much of a year. It's a little bit more than 3 months. You could say in the 3rd month, which is what, in March of 2017. I mean, that's assuming that when they said 2010, they meant on day 1 of 2010. Kind of depends on what you're asked for in terms of how specifically. Is it in what year? What would t equal? In what month of what year, etc. But that's your answer. It's just a matter of formatting it from there. All right, so that is it for us with logarithmic equations and exponential equations, which is section 4.4. I hope you enjoyed it, and I appreciate your watching. Thanks so much.